Okay, so in the previous video, I ended on asking whether L of G, where G was a grammar which we had identified was itself ambiguous, whether L of G was inherently ambiguous. So let me just quickly remind you of what inherent ambiguity is. So I talked about it in terms of general languages at the end of the last video, but we can, for the purposes of this discussion and in the class, we're just dealing with ambiguity in uh, as a notion for context-free languages, right? Because if you think about more sophisticated context-free grammars, then you have to sort of redefine what ambiguity is. We're going to stick with context-free languages. So a context-free language, L is inherently ambiguous if there does not exist an ambiguous grammar of G such that L of G is equal to L. Or in other words, we can also restate this as for every context-free grammar, I guess, an ambiguous context-free grammar. For every context-free grammar G, um, if L of G generates L, then G is ambiguous, right? So here we're dealing with notions of ambiguity, like I said, in terms of context-free languages and context-free grammars. Okay, so and now we're asking this question about the grammar, the language generated by the grammar G. So um, so in this case, what is L of G, right? L of G, just as a reminder, was this guy. So this is L of G. Okay. So this is L of G. Oops. Come on. Okay. This is L of G. Um, where I'm not going to rewrite it, but the grammar that generated L of G was this guy. Okay. So this grammar was definitely um, ambiguous. So now what we want to determine is we want to determine whether or not we can create an unambiguous grammar which accepts the same language, so namely L of G, right? So you'll remember that the reason why, um, well, the reason why I had the way that I had shown, sorry, the way that I had shown that G was ambiguous here, right, in this exercise, was I had said, well, notice I can derive ABA in two different ways. And that really just has to do with the fact that I kind of have a redundant derivation rule, where this derivation rule is actually not needed because um, if I want to generate directly ABA, then I can just go through this step of, first generating the A and then the BA, right? So I can just notice that, right? I can just say, well, or the other way to notice that is to say, well, A star BA or ABA, this is actually equivalent in terms of notions of regular expression equivalence to A star BA, right? Because if I concatenate this with this, like this regular expression fires, if I have one A at the front, or if I have, zero A's at the front, or if I have any number of A's at the front. So this extra ABA thing here is just kind of redundant, right? So you can sort of simplify this regular expression as A star BA, right? So what this tells me is, I'll just um, sort of make the production rules of the first variable, of the S variable, um, directly account for this simplification, right? So what that means is, from S, I can still generate any number of A's. And then at some point, right, at some point, I need a BA, right? This thing fires if and only if there's a BA at the end. So the BA firing would be, generating this final BA and then moving to the variable A. Okay. Okay. So now, maybe that's it, right? So maybe that was the only thing that sort of caused ambiguity, right? Um, so I guess I would just ask you to again pause the video and try to think, is there still a problem here, right? Is this grammar, have I sort of eliminated all possible ambiguity, right? Okay, so hopefully you've taken the time to look at this grammar a little bit before unpausing the video. And so not obviously, but it's very likely that given that I asked the question, the answer was, yeah, there still is a problem, right? Okay, so what is the problem? Well, now it's no longer to do with this guy, right, with this line. It's actually to do with the generation with this guy, right? So what I want you to think about is imagine you want to derive um, something like BA and then A2, B3, right? So how do you derive this guy? Because we know this is in the language, right? The language is, A star BA and then AN BK where K is between N and 2N. So this is definitely in the language, right? Now, what are the ways to derive this, right? So, I can start with S, then I use this BA, right? So now I'm at A. And now, well, what's one way of doing this? Well, I can just say, I have uh, one A here, and then I have two A's here, sorry. I have two A's here and three B's on the right. So let me, first generate the one A, and then let me generate um, the other A, where for the first one let me just write it. Jeez, too much talking, not enough writing. So let me first replace this A with AAB, and then let me again replace it with, let's do well, now I need to replace it using this guy, right? So then I add this extra A, and then I add two more B's, and then I have A, and then I replace that with the empty string, right? So then I get BA and then A2, B3, right? But notice nothing is stopping me from changing that order, right? So I can definitely do something like BA gives me A, and then BA gives me, let's do this other order, right? Let's do this other order. So let's do A, A, B, B, and then BA, A, A, B, right? And then let me replace this with epsilon, so I get BA, A2, B3, right? So both of these are, um, you can think of these as rightmost derivations, right? Both of these are rightmost derivations, or you can also think of them as leftmost derivations. In this case, the rightmost and leftmost derivations are the same because there's only one variable at any given moment, right? So you can call the only variable there leftmost or rightmost, it doesn't matter, right? It's the same. Okay, so what that tells me is there's still a problem in terms of ambiguity, and that's the fact that I can sort of choose at any given generation point that I can use this guy or this guy. Okay, so the common trick to use, and this is just a heuristic, like this doesn't always work. In fact, um, there is no algorithm that takes a context-free grammar and converts it to an ambiguous grammar. That problem is sort of undecidable. So it's not even that it's like very difficult, like NP complete, it's that it's undecidable. So there isn't a general purpose algorithm that will work for all possible instances. So this is why it's just a trick. Sometimes it fails, right? So the trick here is um, if you have something like this, right? If you have something like this where you can either use the first production rule or the second production rule, and these guys can be interchangeable, then the trick is to sort of create two levels, right? So create two levels where the first level, so you sort of split the logic into two levels where you have to use uh, sort of the first derivation rule at the first level, and then the second derivation rule at the second level. So it kind of forces you to use all the possible derivation rules uh, first here and all the other possible. So it forces you to sort of it sorry, it avoids um, this sort of interchange, right, between using this or this, because you have to, so if you sort of split these two things into two sort of different levels, then you first have to go through this guy, and then only when you're done this guy generating this guy, then you go to the next level and generate using the other production rule that's sort of split on a different level, right? Okay. So again, a bit too much rambling. I should have just written this. So really what I just wanted to say is we'll just split the logic for generation onto multiple levels. And by multiple levels, I just mean multiple different variables. So if you think of the parse tree, instead of having sort of um, if you think of the parse tree, instead of always having the same variable, you have to sort of have the variable A, and at some point you have to switch to the variable B, and you can't go back to the variable A. So that's kind of what prevents you from this interchange now. Okay, so what is that going to look like? So instead of having these two guys at the same level, right, at the same variable, then I'm just going to say first generate all the A for B's. And then at some point, decide that you need to start generating the uh, a pair of B for 1A, right? So move to this decision here, okay? And then eventually decide to terminate, right? So if you also add S with AS and then BAA, then altogether, this is actually an ambiguous grammar for um, L of G, okay? And so some of you might be wondering, well, I'm not super convinced, right? If I were you, I would say, well, I'm not super convinced that this like fixes it. What tells me that I can't sort of use maybe two A's and then three B's, or three A's and then two B's and then get the same string, right? Well, this is just a property of this language, in fact. So this is just a bit of an aside, right? Which I won't go too much into, but um, imagine you have AN, BK, where K is between N and 2N. And let's use like two integers. So K1 is the number of times you use the production rule of this guy. So 1A for 1B. And K2 is the number of times you use this other production rule. So two B's for 1A. Um, yeah, let's abstract away this. So 1A for 1B. Come on. 1A for 1B, and then 1A for two B's. Okay. Then the number, like this total, right? If I have K1 and K2, the sum of K1 and K2, that has to be N, right? Because that's always, so that's K1 and K2, the total is just the total number of A's I have in my string, but that's AN, right? So I know that K1 plus K2 is equal to N. So I have this first equation. And I also know, what do I also know? That here, this guy, right, this K, the value of K is equal to the number of times I use K1, right, times 1, because I'm just, like, K1 just means I'm using um, K1Bs, right, plus uh, K2 times 2, because if I use like K2 three times, it means that I add 3 times 2 B's, right? So the second equation that I get would be something like K, so this K here, the number of B's is equal to K1 plus 2K2. And so it turns out if you do a bit of algebra, you can actually show, you can show that K1 and K2 are unique, okay? Um, and so that tells you that there's only one sort of sequence, right? There's only one um, number of ways of using uh, sort of this production rule and this production rule to get the string that you want. So that just means that it's impossible to say, use like this production rule twice and then this one three times, get some string, and then use this one three times and this one two times, get another string, and those two strings being the same. So that can never happen. So because we've sort of fixed the ambiguity for this ABA thing, and we've also fixed the ambiguity for this thing, now there's no other chance for ambiguity or ambiguous derivations in this grammar. Okay. Um, and so yeah, that's just like a brief aside to just show you that this is indeed an unambiguous grammar, and so that's why, so therefore, L of G is not inherently ambiguous. And just maybe a final thing, this is just, if you're still watching the video and you've sort of watched so far, then I might as well give you like a fun fact. So you might be thinking like, who cares about ambiguity? So in fact, ambiguity is actually very important in a few areas. So first of all, in linguistics, um, ambiguity and determining whether uh, some language is inherently ambiguous, that's an interesting sort of research question that linguists care about. And um, it also is important if you're trying to sort of model computationally the production, the generation of sentences in the language. And it's of course also very useful in terms of like programming languages, because it turns out that um, the the syntax of programming languages are defined using context-free grammars. And if those context-free grammars are ambiguous, then it might mean that there's two sort of different ways to parse, let's say, an equation, meaning that, you might parse something like 1 plus 1 times 2. You might get one parse tree that uh, takes the 1 plus 1 and then multiplies it by 2, right? So that would be wrong. Or you have one that does the right thing and first does the multiplication and then does the addition. Okay. So making sure that the grammar you use to model the syntax of the programming language is unambiguous is very important when you want to sort of correctly parse um, the some program that you've written in, Python or whatever. Okay, so fun fact for you. Hopefully that was interesting, and yeah, see you next time.